Hello, everyone. In the last class, we were discussing about the decision hyperplanes for diagonal covariance matrices, where we assume that these covariance matrices are same across all classes. That's the constraint we have taken, and we are looking at how do they look at, and then we arrived at an expression like this: Gij of x bar equal to so and so. Here, in addition, we also made not only the sigma I equal to sigma, same across all classes, but also we assumed that it's a diagonal matrix with the value being sigma, sigma square covariance matrix. So you would say sigma square along the diagonal, right? With those assumptions, we arrived at this expression for a hyperplane where Gij of x bar is equal to mu I bar minus mu j bar whole transpose into x bar minus some x naught bar, right? Decision hyperplane, we know that Gij of x bar value, what should be its value on the decision hyperplane? What should be the value of Gij of x bar?
0.
0, correct. So that means anyway mu I bar minus mu j bar whole transpose cannot be 0. So x bar should be equal to, if you call this whole term as x naught bar, so x bar should be equal to this x naught bar along the decision hyperplane. Of course, if it is a 2D, it's a plane. Anything more than 2D, you may call it as a hyperplane. That's one observation. The second observation here is mu I bar minus mu j bar whole transpose into x bar minus x naught bar is 0. That means these two are perpendicular to each other. So that means x naught. So you draw here, the decision hyperplane is given by x bar equal to x naught bar, and that is perpendicular to mu I bar minus mu j bar whole transpose. This was the drawing that we have drawn there also in the previous class, where you consider that there are two feature vectors here, x1 and x2, and let mu1 bar and mu2 bar give you, like for example, for mu1 bar, this is x component, y component, it's a vector of 2 cross 1. Similarly, this is mu2 bar. Now, what would be mu I bar minus mu j bar? Easy to do that. So minus mu2 bar is in this direction plus mu1 bar. So this would give you mu1 bar minus mu2 bar. First thing. Second thing, it has a value at x bar equal to mu1 plus, assuming that p omega 1 equal to p omega 2. So that means this term would become 0. Then your x bar equal to half of mu1 bar plus mu2 bar, right? So that's the value along the hyperplane. And if these two vectors are given, you could also figure out that mu1 plus mu2 by 2 will be on this line, one possible value. So it passes through mu1 bar and minus mu2 bar, and also this is perpendicular to it. There you just mark what is mu1 plus mu2 by 2. Simple vector calculus of drawing mu1 plus mu2 will help by 2 will help you to figure it out. And then this is perpendicular here, right? And it is equidistant along this line if you measure to both mu1 and mu2, because you are taking half of that path. Okay, this is the line connecting them. It is half the distance from both. That's why we identified one point there, right? And then we discussed, suppose if probability of these classes are not same, assuming that omega 1 probability, prior probability for class omega 1 is more than the prior probabilities of class omega 2, then whichever class has more probability, this decision hyperplane would be moving towards that. So that's something we have worked out. Okay. So after this, so shall I continue from here or any questions from here? This is the decision hyperplane that separate both these classes. Now, for some reasons, we are making here an assumption about probabilities of omega 1 and omega 2, where there could be some errors in our estimation. Because of that, forget about in which direction it moves, but you could for sure say here, okay, even if you do not get that, that this will move and this will be still perpendicular to your mu1 minus mu2 vector, mu1 bar minus mu2 bar vector. Now, this all you could say for sure is depending on omega 1 and omega 2 values. If they are not equal, accordingly, depending on their ratio, it will move in that particular direction. So now, if you have even a small error in your assumption, or there is some noise added to your system because of that, you got these values, you are computing, estimating mu1 bar and mu2 bar from a given data set. So there could be some errors. And how sensitive your classification will be to these errors, you could say it based on its variance values. Assume that until and unless it is around the 2 sigma value, if you are plotting it as a circle there. Okay. So you could see here, this is mu1. Around mu1, you have a distribution there. I'm plotting one iso contour, let's say 2 sigma or even 3 sigma, I'm plotting it. Then you could say here, this is in between these two on this line because it is mu1 plus mu2 by 2. That means it is in between on this line if you take it, correct? Or accordingly, if even if omega 1 or omega 2 are different, you will somewhere you will figure it out, still perpendicular to that line. But what you can say is this is less sensitive to errors in computing the decision hyperplane. These errors may get introduced for various reasons. As we discussed, one reason could be the very estimation of mu1 bar and mu2 bar. When this variance is very high, then the computation of this hyperplane, decision hyperplane, becomes very critical, and that could lead to more errors compared to the cases where you have it is okay even if your decision plane goes here and there when your variance is small. Okay, is the interpretation till this point clear, or any questions here? An extension of this exercise now, for the covariance matrices are same for all classes. We are still assuming that. Now, what we are relaxing here is that the covariance matrix can be a non-diagonal matrix. That means, another way of saying the same thing is you could expect some statistical dependence between feature vectors. When that is there, we will have some non-diagonal covariance matrices. Well, what would be the implication of it when you are computing all these things is earlier, wherever, if you recollect from the previous class, you could see wherever there is sigma, or the class before that, wherever there is this covariance matrix, this inverse of it, we are simply writing it as 1 by sigma square into an identity matrix. You could do that only when your matrix is diagonal. This is non-diagonal now. So what would be the impact of that now? You will, so this again, the mathematics follows the same process. So in the interest of time, I have already written it there rather than doing it now real time with a slow response. So it will take more time. So I thought I would do it. Then you could later please do it yourself again. It will serve you as some exercise to ensure that you have understood things properly. I'll anyway, the key steps I would also now explain you the things. Okay. So gi of x bar for non-diagonal elements, what would be that? This is again a expression we are borrowing from the earlier ones, where it is mu I bar transpose x bar is what you had here with 1 by sigma square. Now instead of that, you have mu I bar transpose sigma inverse into x bar. If you are still doubt, just come here and see. Here 1 by sigma square into mu I transpose x bar we have written. But when this is a non-diagonal one, this inverse sits in between. Okay, simple way to mathematically convince yourself on where this should sit, sigma inverse should sit. Just look at the dimensionalities of all these vectors and matrices, as simple as that. Anyway, we did it now for enough times, and now I'm sure you are clear that this would be mu I bar transpose into sigma inverse into x bar. Of course, there is this term natural logarithm of probability of omega 1. And of course, the same expression that we had last time, we were dropping natural logarithm minus 1 by 2 into natural logarithm of this is there. Okay. Similar expression, sorry, not here. Yeah, here. 1 by 2 sigma square into mu I transpose into mu I is there in that. Now what you do, a similar exercise you do, this would sit inside this. That's all. Just figure out gi of x bar. Once you are done, the rest flows smoothly. Now you need to compute the hyperplane. You do gi of x bar minus gj of x bar, and that would easy to write. Mu this transpose I am already taking up, and then you write the same expression with varying subscript j. Then you could figure out mu I bar minus mu j bar whole transpose into sigma inverse into x bar minus 1 by 2 into, well, in one case this is like x square minus a square. We were doing it earlier also, this kind of simplification. So what you get, mu I bar minus mu j bar whole transpose here, and mu I bar plus mu j bar you will get for this x square term, I square term corresponding to I and term corresponding to j. This is more like x square minus y square that has happened. And of course, minus natural logarithm of probability of omega 1 minus natural logarithm of probability of omega 2, you write like this. Now you take out now the term, this whole term you will take it out here till here, right? Mu I bar minus mu j bar whole transpose into sigma inverse will be x bar minus 1 by 2 into, this is already there. So you write mu I bar plus mu j bar minus natural logarithm of this into, well, again, this is the same way you simplify the way we did earlier. So you write here into mu I bar minus mu j bar divided by this whole term in the denominator, right? So now you could think a further one. I want to write, if you remember, it is like the whole exercise we did in the last case is like W transpose into x bar minus x naught bar. That's what you have written. Then you realize that this W is perpendicular to whatever expression is there inside. One thing. Second, this is where the what would be the x bar value there. That also we know, we have figured out for a diagonal matrix. Exactly same thing now you are doing. So I want to write it in terms of transpose here. Simply now what will happen? AB whole transpose equal to B transpose times A transpose, right? So this term would come first, sigma inverse into mu I bar minus mu j bar whole transpose into x bar minus, yes, this is something I want you to draw your attention here. This has been written as sigma inverse norm of mu I bar minus mu j bar. This is very, very important. We already discussed it in the previous classes. What is this distance referred to as? Mahalanobis distance, okay? Where normally if you want, you are given a vector, and if you want to compute the Euclidean, L2 norm will give you the Euclidean distance. Now that is nothing but x transpose. If you have a vector x transpose x will give you the distance. Now what happened? X transpose into, assume this is an L dimensional one. There is an inverse matrix here of L cross L into X transpose. Okay. This is kind of another way of looking at it, is you are applying on this. This is referred to as sigma inverse norm of y bar. Okay, I will bring a little more clarity about this term again further. But for now, you just look at it is, if you are doing mu I bar minus mu j bar whole transpose into mu I bar minus mu j bar. Okay, you call it, if you want it, just call it as mu bar, a single vector. Mu I bar minus mu j bar is another vector of same size. So mu bar transpose into sigma inverse into mu bar. That is nothing but, forget sigma inverse. Mu bar transpose into mu bar is nothing but mu1 square plus mu2 square. So all the corresponding elements in that matrix, you square it and sum them up. Suppose I have mu equal to that one, these are not vectors now, scalars. Now mu transpose mu will give me, well, mu1 square plus mu2 square. So that's nothing but L2 norm square. Okay. And of course, now I have mu1 minus, there is some other vector. Okay, let's call it as mu1 minus mu naught, mu2 minus mu naught. Now this vector, let me call it, maybe I don't know, just call it as P. Now P transpose P, what does that give now? Mu1 minus mu naught whole square plus mu2 minus mu, means there is no reason why these two should be same. So if you want mu01, mu02, you keep whatever you want, minus mu02 whole square. That is nothing but the Euclidean distance between these 2 points. Is this interpretation and visualization clear to everyone? So if you understand this, without that sigma inverse, what you are computing when you are doing mu1 minus mu2 there is the Euclidean norm, Euclidean distance between them and square of them. Now, in addition, what you are doing now is you are applying a transformation on that of sigma inverse. Okay, then instead of doing that, mu transpose into sigma inverse into mu, that is referred to as Mahalanobis distance. And now another observation before I ask you if you have any questions or not is, earlier it is perpendicular, this x bar minus x naught bar is perpendicular to mu I bar minus mu j bar. That's how we have plotted it. Now notice that what is this perpendicular, x bar minus x naught bar? So this expression now is perpendicular to what? Can you tell me to what it is perpendicular now? Are you with me? So earlier in this expression, we worked out that mu1 bar minus mu2 bar, right? It is, the decision plane is perpendicular to mu1 bar minus mu2 bar. Now, can you tell me the decision plane is still perpendicular to mu1 bar minus mu2 bar in case of a two-dimensional vectors there, or is it perpendicular to something else now?
Sir, it's perpendicular to sigma inverse into mu I bar minus mu j.
Correct. Very good. So sigma inverse is like a 2 cross 2 matrix. Mu1 bar minus mu2 bar is a vector. Now, when you are multiplying a vector with a matrix geometrically, this is equivalent to applying a transformation to this vector. You are there in a two-dimensional space. Mu1 bar minus mu2 bar is a vector in this two-dimensional space. You are multiplying it with a matrix of 2 by 2 of sigma inverse is that matrix. That's equivalent to a linearly transformed mu1 bar minus mu2 bar. There is some transformation happening there, and it is indeed perpendicular to the transformed mu1 bar minus mu2 bar. It could have been a rotation depending on the nature of your sigma inverse. It could have been something else. So now this is perpendicular to the transformed mu1 minus mu2. That linear transformation that has been applied will be known from sigma inverse.
Sir, we are multiplying sigma mu I minus mu j transpose into mu I minus mu j. So it should be norm square, right? Norm is square root of, norm is usually square root of square terms. Here, after multiplying, we will get terms, but it should be norm square over there. Yeah.
So you are right. So this is equivalent to actually, it's not just L2 norm, that is square of that L2.
Yeah.
Correct. Very good. Your point is I should have kept here square. Huh? Is that the point you are mentioning?
Yes, so usually we calculate norm after taking square root.
Yeah, that comment makes a sense. Makes sense. It seems correct. Let me. Yeah, very good. Very good. Excellent. I missed it. Very good. I'm glad you have pointed it out. So hope everyone else is also understood that question. See, the distance is square root of x square plus y square. Norm is in fact x square plus y square is what the norm gives. So should not there be a square? That was a mistake from my end in drawing it and writing it up. So yeah, very good point. That's right. Excellent. We are done with this now. Just to again a quick recap. When you have cases we considered here are very special cases where all classes have same covariance matrix. All the classes have Gaussian distribution. And the first case we considered is the covariance matrix is diagonal. Then we had a look at how the decision planes would look like. Then we figured out that these decision planes are such that it is perpendicular to, if mu1 and mu2 two classes are there, whatever classes are there, this is perpendicular to that decision plane. And it would move depending on probabilities of omega1 and omega2. And of course, how sensitive it is to these errors in this decision plane depends on the variance of these classes. That's what we studied in the previous whole summary of the previous class. The summary of the current classes, an extension to that. How about, I still have all covariance matrices same, but I have a non-diagonal. I have a non-diagonal covariance matrix. Then we figured out that this vector, if you consider a two-dimensional case, or for that matter, any dimensional case, this vector mu I bar minus mu j bar is no more perpendicular to your decision hyperplane, but rather it is perpendicular to sigma inverse, a linearly transformed mu I bar minus mu j bar. That's one thing we have seen here. And now we compute these distances in terms of, so here the terms, even when probability of course, when if these two probabilities are same, this term won't be there. This is x, then x bar value will be same, but this is at a angle, not 90 degrees anymore, right? Suppose if they are prior probabilities are different, then the term you have here is dependent on Mahalanobis distance. This is what we discussed in the previous class as well as class so far. If this is fine, I'll move to another topic, perhaps the last topic for your midterm exam. This is the last topic. With this, we wrap up for your midterm exam. And then parametric estimation is what we start from the next class. That is not part of your midterm syllabus. Okay. Now, so far the analysis is based on decision hyperplanes. Now, let us now, anyways, if you recollect the sequence of events we did, we in fact were right away doing the analysis based on likelihoods, or even more general, if assuming different prior probabilities on posterior probabilities. That's what we were doing. If you take a then discriminant function, if you take on it, this exercise we have done along with some examples, that if you apply a monotonically increasing function on that, which we were calling it as GI of x bar, whichever GI of x bar, depending on those values, we could say to which class this belongs to, correct? So this also tells us something. The decision, one way is to look from decision hyperplanes point of view. Another way is to simply look at the discriminant function that you would get for each class for a given x bar. So this is the last part of analysis that we are going to do here. Again, for this, you consider that so that we'll be able to get some insights, a special case where the prior probabilities are same for all classes. And still, of course, the covariance matrices are same. We'll consider that. But we'll consider we'll start with the diagonal covariance matrix, then we will move to non-diagonal covariance matrix. Now, let us write the expression for discriminant function for a class I for a given vector x bar. That is nothing but minus 1/2 into x bar minus mu I bar whole transpose into sigma inverse into x bar minus mu I bar plus natural logarithm of probability of omega I. Hope you all remember how we arrived at this. If you have forgotten, I'll just remind you, like probability of x bar, you could have written like 1 by 2 pi square whole to the power of L by 2, right? Into this determinant of 1 by 2 into, in the denominator you have, for numerator you have minus 1 by 2 into, I'll write first for a 1D case, then you x minus mu whole square I'm writing, that you could, if it is an L dimensional space with a covariance matrix, that is nothing but x minus mu transpose into sigma inverse by sigma square is there. The sigma inverse would come there by 2 sigma square. 1 minus 1 by 2 anyway I have written. So that sigma, yeah, the sigma square is nothing but sigma inverse. It's a covariance already, so that square won't be there. So then, yeah, this is a likelihood 1 into probability of omega I is there when you are writing it. So you take logarithm, then we defined our monotonically increasing function by taking logarithm of it. Then we dropped functions that are common, that has dropped this root 2 pi. And anyway, covariance matrices are same. So this determinant of sigma function got dropped here. Then all we were left with this thing. Okay, I just made a kind of a quick summary or recap of how we arrived at this. This is not we are doing it for the first time, but I'm just giving you a pointer. And now, if you still hope that helps you to recollect, if not, please go through my earlier classes videos. There we have properly worked it out. Hope you all are able to recollect this. I want to ensure that, because we are going to draw some inferences based on that. First thing, so this is the term. Now, I further assume here that all classes are equally probable. So I could redefine my GI of x bar such that this doesn't, this term also, this can be, oops, this term can also be dropped here. This term can be dropped here. Okay. Now consider a diagonal covariance matrix. That means sigma square into I could identity matrix you could write. That means sigma inverse will be 1 by sigma square into I. You put it here. Then DE, Euclidean distance, is x bar minus mu I bar whole transpose. Okay. So that's what, because you have got it as x bar minus mu I transpose into x bar minus mu I bar. How would you make now assignment to the classes when you have this GI of x bar? So essentially, if you look at these classes, what would happen is, this is nothing but now, let's say you have x1, x2. Let's say this is your mu1, mu2, right? You have somewhere a line joining this. This is a diagonal matrix. So you draw a line perpendicular to it. That's your decision hyperplane. What you have computed right now is GI of x bar. Now you assign it to a class that has minimum Euclidean distance. That is what you are going to do here. Why minimum Euclidean distance? GI bar should be maximum, right? Why am I calling it as a minimum Euclidean distance? Should it not be maximum? Because if you recollect, even from probabilities, the term has to be maximum. All of a sudden, I am saying here, assign, you calculate it for each class and assign it to that class which has minimum Euclidean distance. Why this sudden shift has come in my statements? It is a monotonically increasing function. Hope you are all following my sequence of arguments or statements I am making. I'm suddenly saying now, you compute it for all classes. What are my classes here? GI of x bar I refers to a given class. This I can take any value from 1 to m. Now I'm making a statement that you assign it, you calculate GI of X bar. I have got this expression here, -1/2 sigma square into Euclidean distance whole square. Now I'm saying whichever has a minimum Euclidean distance, you assign that X bar to that particular class. Can you help me with that statement? Look at this sequence of statements we have built. You want to maximize multiplication of likelihood and prior probabilities. That will give you the posterior probability, maximizing posterior probability. So if you recollect from the very beginning classes, you calculate the posterior probabilities for all classes, whichever has maximum, you assign it to that maximum. Now suddenly it has become minimum. Now I have taken on top of it a monotonically increasing function. Okay. Then while comparing anyway, common terms all I dropped it out. And suddenly I'm saying you pick that which has a minimum Euclidean distance instead of saying maximum now.
Sir, the prior case was in terms of probability, and
Right.
this term is in terms of distances. So minimum the distance, more is the relatable.
You see,
Yes.
there is a maximization problem is there for me. All I did is I applied a monotonically increasing function, not decreasing function. So that gave me this expression. Pay attention to this expression. The answer is in this expression itself, where I have d square. So I should maximize this expression, but all of a sudden I'm saying you take a minimum Euclidean distance.
There's a negative sign in the expression.
Right, very good. Even before answering that, the first thought that came, this I did not realize while I was writing the notes, but then I realized that there is a negative sign there. So if you minimize this, then among the classes that would be maximum. So that's why, of course, when since some of you had physically visualized what it should be, you have aptly figured out that it should be minimum. But to make it equation wise also sense, this is because you have a negative sign there. Hope you guys are with me and realized this small nuance here. So that's why all you need to do now, similar to what you did initially with probabilities and Bayesian theorem, before you apply or come up with any discriminant functions that are monotonically increasing in similar lines, all you need to do is, if you have a diagonal covariance matrix, same for all classes, you are given an X bar, and your job is now to assign this X bar to one of these classes which are characterized by their mu I and sigma diagonal matrix. All you need to do is, for each mean vector, of course, mean vector will be same size as your X bar, compute the Euclidean distance and assign it to a class that has minimum Euclidean distance. That's the message here. Any questions or doubts here? So just here you are, for any given point, you compute the Euclidean distance and assign. That's all it is happening. So of course here, this term, if you look at it from the mean vector, if you are calculating and drawing an isocontour, this term being same would give you the same value of GI, which means same Euclidean distance means we'll get circles there. For any given point, just compute that, and whichever it is close, you simply assign to that. That is all happening when you have a diagonal covariance matrix, same across all classes, and your prior probabilities are same for all classes. Let me then move on to the second, slightly generalized case, where instead of a diagonal covariance matrix, I have a non-diagonal covariance matrix. Then what will happen? In this expression, I could still drop this term. Now looking at maximum of this means, of course, if you change the sign here, minimum of this. Now earlier, your Euclidean distance is X bar minus mu I bar. Now minimal of this term we have already defined as Mahalanobis distance, which is X bar minus mu I bar transpose into sigma inverse into X bar minus mu I bar. And that is what, of course, it's just a square. It doesn't really matter. It's positive while you're comparing. You could, and in fact, you would directly square of the Mahalanobis distance is what you compute, because you could by that avoid even computing the square root. You just do that. Okay. So the message here, so you now compute the Mahalanobis distance instead of Euclid. If you have a non-diagonal covariance matrix, you know the mean values for all classes. You know the value of sigma also, which is common across all but non-diagonal. Now, if given an X bar, to which class should I assign it? All you need to do is, instead of computing a Euclidean distance now, compute Mahalanobis distance to the mean vectors of each class and assign it to that class which has the minimum Mahalanobis distance. The next question I pose to you is, how does the iso contours of this Mahalanobis distance, same Mahalanobis distance points or vectors in the x1, x2 space would look like? Well, it is a non-diagonal matrix, but also remember, it is a symmetric non-diagonal matrix. If you remember the off-diagonal elements, they are the same, okay? Sigma ij equal to sigma ji. So based on that, what you could do is, this is an L cross L matrix. Sigma is a L cross L matrix. You need to take inverse of it. Okay, you go through the standard matrix linear algebra, where you could write it as, this being a unitary transform will give you something like this, a phi, you call it gamma or delta, I don't know, into phi transpose. Phi transpose is equivalent to phi inverse. This is a diagonal matrix. The middle one is a, this one is a diagonal matrix. So in this form you could write, and then if you substitute it here, that one, what will happen is, you would realize that, yeah, I'm skipping the math. You could go through it. It is there in the textbook. But you would realize that this is a transformation, and on mu1 and mu2 is applied, and to that transformed mu1 bar minus mu2 bar, this will be perpendicular. Now, this line, whichever was perpendicular to mu1 minus mu2, now this will be perpendicular to a transformed mu1 minus mu2. That's what would happen. And these, in fact, would give you ellipses. It is not, and the eigenvalues will be the diagonal elements of it. In the interest of giving actual insight into it, and maybe if I have to explain this, I need to write all these eigenvalues and eigenvectors, and then the diagonalization to find inverse. These things I need to, and the transformation I need to explain. But since I'm not very sure how many of you have it on top of your mind, all these things, so I may get stuck there. So rather to deal with it in a mathematical way, which you could refer to the textbook, I just want to convey you the intuition and the final result here. What would happen is, this would not be any, this will not be any more perpendicular. This is already clear, because it is not simply mu1 minus mu2, but sigma inverse into mu1 minus mu2. To that it is perpendicular. And that space, you could look at it in a different way, and you would realize that you would be getting an ellipses here. And those will be, those ellipses means there are no more circles, because the transformation in mu1 and mu2 that you do could be different here. That's what you would realize. Because of that, this circle would become ellipses, and also rotated ellipses. That's what, because it's equal into that will be equal to rotational, multiplying with a rotational matrix. And then these are the things that you get it. So if you have an example, worked out example also in the textbook, you could refer to it. But anyway, in the exam also, I will not ask any problems for you where I have a non-diagonal covariance matrix, as I'm not very sure how many of you are very comfortable with it. But again, it is not to say that you can get away with it. Later point of times in this course itself, we may discuss, or even irrespective of this course, I would strongly recommend you to get that mathematics also very clear, as it will come in a varied forms in various places or in various subjects. So go through it. But as far as the exam is concerned, I'll not ask you anything about this part, but I could ask you about any other thing there. Okay. Is it clear now about the non-diagonal covariance matrix? So here you have circles. Now this you instead of that, when you multiply this with sigma and everything is there, this gets an ellipse as well as rotated ellipse. With that, this will be no more decision. The equicontour points will also move there. And what you look at now is to given an x bar to which class to be assigned. For that, what you are going to look at is not Euclidean distance from the mean vectors of each class, but rather the Mahalanobis distance from the mean vectors of each class. That's the take home message here. Okay, good. So with that, your course is for the midsem syllabus exam is done. So there are just a few remarks I could make also, but anyways, that doesn't matter for now. So if you want it in terms of the textbook, well, there is in your textbook for the, particularly for Bayesian classification, we have covered till section 2.4 in this Sergois Theodoridis textbook. So if you go through this textbook also, you go through some additional problems that have been given, and you try to get very comfortable with concepts as well as application of the concepts. That's as far as your syllabus is concerned. Since we have some more time of 10 minutes, I would like to solve one simple problem here. Particularly for this diagonal covariance, the minimum distance classifier. How do you do a classification given this a diagonal covariance matrix? Okay, so let's work out some example. Again, this example is also from the textbook only, but let's work it out. Let's assume we have two classes. That means m equal to 2. I have a feature vector of size 2. That means x1 and x2, so that I can easy to keep track and visualize also. So I would consider L equal to 2, and my sigma 1 and sigma 2. Anyway, yeah, this sigma 1 equal to sigma 2, because that's all, then only all our calculations are valid. Only when you have equal covariance matrices. So this I would take it as 1.1, 0.3, 0.3, 1.9. This is my covariance matrix. Now I am given the what else are required to make the calculations. I should also know the mean vectors. I should know. Let the first one has a mean at 0, 0. That means at the origin. And the second has a mean at the whole thing got shifted to 3, 3. So same circles there, but shifted there. Now you are given a feature vector x bar, which is equal to 1.0 and 2.2. What I wanted is classify x bar according to the Bayesian classifier. What should I do now? Tell me, which distance should I find out? And minimum of those distances I could assign. Which is the distance that I should consider here? Euclidean distance or Mahalanobis distance?
Mahalanobis.
That's all. Okay. So Mahalanobis distance, I require inverse of my matrix. So sigma inverse. Okay. It's easy to 1 by AD minus BC into D minus B minus CA. The standard one will give me 1 by AD minus BC will give you 2 there into D. Interchange of the diagonal elements 1.9, 1.1. Change of sign for the off diagonal elements minus 0.3, minus 0.3. And that would give me 0.95 minus 0.15, just taking half of the values as I have outside 1 by 2, and here 0.55. So how do I compute Mahalanobis distance now? Or I would rather compute square of the Mahalanobis distance. That way, so that I don't have to find out square root. What is that? Tell me in terms of x bar and sigma inverse.
Minus mu1 bar
Yes, I will write mu I, so that later I could put any of this.
transpose
Yeah, into whole
transpose
transposer. Very
into
good,
sigma inverse
right?
and
Into
to x bar minus mu I bar.
that's all. Okay. Now, now if you compute that dm square for I equal to 1, you just substitute them. So x bar minus mu1 you take them. The second one mu2 you take them and compute. For I equal to 1, you will get it as 2.952, and this for I equal to 2, the second class would be getting 3.6672. That means assign x bar to,
First class.
that's it, assign x bar to omega 1. Very good. That's all. Okay. Any?
So what if both the distances come out to be same? Then what should we do? Assign it
Yeah,
to
it's a very tricky thing. Then you could assign it to any of the classes, because that is a that means it is exactly on the border, right? It tells you that it is exactly on the decision plane, is it not? So you can then means each has equiprobable, each of those classes are equiprobable. Finally, even when you look at the likelihoods and prior probabilities put together, so you could say it cannot be decided, or you assign it to either omega 1 or omega, that which is very unlikely case. But that's what of course would happen along the decision plane. If that point I given you x bar is along this decision plane, that is when you get both to be same. Is it not?
Yes, sir.
Right, good. Yeah, so the next, but this is again worked out example from textbook itself I've taken. Second one is there where they have more related to this part to compute of the isocontours of these values, that I skip. You can also skip it for from the exam point of view. Okay. If you don't have any further questions, this is where we will stop, and